All right, here's part 2 of the video for class 4 that I was making today. I wanted to walk through a couple examples that we didn't get to in class, or I didn't do what I felt was sufficiently in class. So here we go, move on to do it in one note. All right, so here's the problem, and I'm just going to walk through it as opposed to writing all of this down. This is a polar coordinates problem, and the setup for the thing has a little bit of a oddity that the radius, or the r value right here, is a function of the angular position. So really the procedure that I would recommend for most polar problems is to try to figure out what the variables of interest are right here. So that's what I say here is the best approach to find these VOIs. So we were given this angle right here, and we're given this, and we're told that we're given this angular velocity. We're told that it's a constant angular velocity, so that means that theta double dot is 0. The rest of these three we are to try to find out and figure out just by the relationships, the kinematic relationships. So first off, we can just plug in theta, which we were told was 45 degrees. If we do that, we end up finding that it's 0.75 meters. The next, and this is just a little different right here, we want to try to find r dot. Well, we could do that by finding what this is, the derivative of this with respect to time. In order to do that, we need to, because it's in terms of theta and not in terms of time, we need to take the derivative with respect to theta and then multiply it by theta dot. What in essence we're doing is we're taking the derivative of it with respect to theta and then multiplying it by d theta dt, recognizing that this right here is theta dot. So that's what I've done right here, is multiplied that. So what we see in this part right here is this, the derivative of this whole thing with respect to theta, and then we're multiplying it by theta dot. And we can also, so we get it in this form that's still in terms of theta, but we could also plug in the 45 degrees and the known theta dot, and we could find now we have the value for r dot. Now we take the derivative, the time, or well, we take the position or the angular derivative of this, and once again we need to do that theta dot trick. So and because there's multiple terms in here, the theta dot and the 2 theta in there that are in terms of theta, we need to make sure that we account for, we did the product rule here. First off, so we go through and we take the theta dot and we take the derivative of that with respect to time. Well, that's just theta double dot. And then we take, need to take that 0.5 times theta dot right here and multiply it by the time derivative of sine 2 theta, which is going to be 2 cosine of 2 theta. But that's with, once again, with respect to theta, we need to once again use this rule over here, so, and we apply the theta dot. Plugging in numbers, we get the very boring thing that this actually equals to 0, because the first term, theta double dot, is 0, and the cosine 2 theta, 2 times 45 is 90. The cosine of 90 is 0, so that ends up being 0. So right down here, we could do the summary of our variables of interest. And once we do that, we can plug it in to the standard form for polar velocity, which is r dot as the coefficient of ER, and r theta dot as the coefficient of E theta. And this is what it would look like as a vector in ER and E theta. Most often, though, we would like to get the magnitude, the overall velocity of the thing. So we take the magnitude of this, and we're able to find that value. noting up above, it did ask, was it determine the magnitude? Yes, so that was what was being asked. Quite often we also want to know the direction, and that direction should be with respect to the x-axis, the horizontal. That's just the normal convention. We have to be careful when we're doing that we might need to do a coordinate transformation to get it back into the x and y directions before we try to get the angle. Otherwise, we have to compensate for the whatever coordinate system we might be in. For instance, if we were to try to do the direction, we might be tempted to, and I'm going to use like a beta here, not to be confused with theta. We might want to take the inverse tangent of, let's say, rise over run. In this case, we might associate the e theta with the rise. So we might go 0.375 and 0.25. The trouble with that is that this is going to give us an angle with respect to the theta, right? So like we're already on this plane right here where this is e theta and this is ER right here. So what we're really getting is an angle. This beta is right here, right? So if we were, and so right there's the theta that we found to be able to get into this position. So we just have to be careful that where we're looking at. So one way of being careful is to just turn this back in to I and J, and then find what the angle is going to be. Now, all right, so here the second part of this is to find the acceleration. And once again, from our variables of interest, which we've summarized right here, we could just go ahead and populate this equation. Several of the things are going to be 0 in this case. R double dot is 0, and theta double dot ends up being 0. But there's still other terms in here, so that we end up with an acceleration. And the question did ask for the magnitude, so we're able to find what that is. Similarly, we'd have to be careful if we weren't only asked for the magnitude, and we were asked for the magnitude and direction. We'd have to be careful, like I said before, about what angle we reported, because in general we mean with respect to the horizontal. Now here's a problem that we did previously at the Coast Guard Academy, and I liked this problem a lot. I think it's still in the textbook. I wish there was more problems like this, because it is a very practical thing. That previous problem, it is not necessarily something that we're going to do all the time, but this is more along the lines of a kind of a question I like. So this airplane is taking a big old dippy, and it's got this big bottom of a loop. I hope I'm not on this passenger plane while it makes a loop. But it's making a loop, and when it's at the bottom of this loop here, it's going 300 miles per hour, and it's speeding up, right? So that's an important thing. It's speeding up. That's a particular kind of acceleration. That's the tangential acceleration, right? That's speeding up. But it's in a loop, therefore it has normal acceleration as well. We can find that normal acceleration, right, is going to be v squared over rho. And the radius of curvature is 1 mile. The plane is being tracked by this radar. Now, this radar is doing things in terms of a distance away and an angle from the horizontal. That, by definition, that is polar coordinates. So this is finding this in polar coordinates is very applicable, or I should say, it's kind of a standard thing. This radar thinks in terms of polar coordinates, so it makes sense to report things in polar coordinates. But we want to make these two things that are happening. One is in tangential and normal coordinates, and one thing's in polar coordinates. So we want to make sure that these things are compatible. So this is me working the thing out already here. What we could do is do some units conversion and figure out what the tangential velocity is in feet per second, as opposed to having in miles per hour. Figure out what the radius is of curvature. That's 1 mile or 5,280 feet. That's something worth memorizing. We can figure out what R is. Okay, so that's just going to be the rise and the run. Or I should say rise and run. I just did those backwards. And we can find out what theta is by taking the inverse tangent of the rise over run right here. So we notice 36.87, but I like to use things in radians sometimes, especially in Excel. Makes it easier. They already gave us the tangential component right there of acceleration, and we could find the normal, like I said before, by finding the v squared over rho. So we have this information, and what we could do with this, just to make this clear, we could, and I didn't do it here, we could write that the acceleration, by the way, I'm writing on this thing as in laptop mode, so it's going to be kind of ugly. So here's my acceleration. I could write that it's going to be 10 ET right here plus, and then 36.67 EN. All right. Now, what I've done afterwards, after this point downwards, is my standard way of, well, it's also what the book does quite often, to try to reconcile the components of something. Another way of doing it is to take the coordinate transformation. And we kind of see sort of a similar setup right over here. But let me try to do the formalized thing that we would normally do here. All right, so we make a little table for this. Didn't do a great job of this. And this right here is the ET, and here is my EN. And they got hats. So let me write ET and EN. And then we also, like looking back over here, we could see these coordinate unit vectors. So I'll pick something like green, and we can go boom, boom. And so this is going to be ER, and this is going to be E theta. So we go ER and E theta. And then we start looking, okay, here's where the theta is going to be. Here's another theta in here. So we start to pick it apart. We go ER can be broken down into, it's going to be the cosine of theta in the ET, and it's going to be the sine of theta, because it's like right here, that part of it, in EN. And project E theta onto ER. It's going to be negative, right, because it's going that direction right there, and sine of theta, because it's, you know, right opposite from the angle. And then similarly right here, it's going to be in the positive cosine right there. So there's your transformation matrix, and what we could do is we could apply it right up to this guy up here, and turn these into ER and E theta coordinates. But I've done it just by piecing it together. Right up here, we had that our VT that we were given, right? There's only got one part of the tangential thing. So I could say that it's, and I know this theta is part of right there. So I could just project that onto my ER right here. And I know that's going to be my, let's call this is the VR right there. It's going to be R dot. And then so I took the cosine of this angle right here and multiplied it by my VT so I could get this. And then I took V theta right here, and I was able to find it because it's in the negative direction here of my VT, right? So, and I'm able to turn this and find this component right there. So now I'm actually able to write those out. And from this, okay, I know that this v theta is r theta dot. And from that, therefore, I'm able to find what theta dot is. So you can see there's a little bit of we're proceeding through a logical step and trying to figure out like all the different components and their contributions and where they came from. And then from that, we're able to deduce what theta dot is, because we know that v theta component has theta dot r in it. So we're able to find this. Once again, we're looking for our variables of interest. We were able to find r dot from our VR, and we're able to find theta dot from our v theta. And then, okay, so now we can go with our accelerations right here. We can also look for, by doing a coordinate transformation, if we were to do this process right up here over to this, we would come up with and find what the AR and A theta are. All I did was over in here in my little thought cloud was to break them apart piece by piece. But we could also do the coordinate transformation. And in doing that, we could find, because we know we could find what R double dot is going to be. R double dot is inside the AR, because I was able to find the AR just by checking the coordinate transformation, and now AR is going to, we have a value for it, and we also know R, and we know theta dot squared, so we can find R double dot. And then in a similar way, we have a value for our A theta, so we're able to and we know what R dot is going to be, and we know what theta dot is going to be, so we're able to find theta double dot. So we're able to get all of this information right here in these variables of interest. And so you can see this is kind of an interesting thing, because so this is what we're predicting that the radar is going to detect, because it thinks in terms of polar coordinates. So there you go. There's some more examples, ones that I wanted to get to. There were other things in the notes that I thought were kind of cool. I encourage you to go to these mechanics interactives that are part of the book, and you can kind of see the thing. This is a ball spinning around. You can see what the components are, turn the thing on and off. Maybe that'll help you visualize some things. There's also some videos. I've posted the links on Blackboard, and I encourage you to go to these. These are also from the publisher, and they can help you to look at the problems or look at these coordinate systems in a different way. So that's all I have. Thank you.